Our speaker today is Ellis Monaghan from the University of Amsterdam. She works in algebraic combinatorics, especially graph polynomials, applied graph theory in DNA self-assembly, statistical mechanics, computer chip design, bioinformatics, and mathematics pedagogy. She is an editor-in-chief of the Primus magazine, and editor of several other magazines. Our talk today is on new dualities from old. Thank you, Joe. The stage is yours.
All right, so let's do a little screen share here. And so, yeah, if folks have questions, feel free to holler. I tried, yeah, everybody always says this and it's never true, but I'm going to say it too. I tried not to overpack the talk and we'll try not to rush at the end. Yeah, we'll see. But anyhow, feel free to give a holler. This is joint work with Lowell Abrams. So, so what we're looking at here are graphs on surfaces. We're looking at cellular graph embeddings and duality, usual geometric graph duality, looking at Petrie duals, looking at the Wilson group, which is the action of taking duals and Petrie duals on embedded graphs. We're also going to be looking at partial dualities and trialities, which in aggregate, for lack of a better term, not for want of trying to come up with a better term, we've been calling dualities, and self-tool graphs. The big question is effectively generating self-tool graphs, being able to generate graphs with desired kinds of duality or Petrie duality or triality. So that's what we're after. All right, so cellularly embedded graphs. All of the graphs we're going to be looking at here are cellularly embedded, so the faces are two cells. This top one is an example of a cellularly embedded graph. So it's a graph drawn on a surface, on a smooth surface, with the property that if you remove the points of the graph from the surface, the complement, the bits that are left, are all disks. They're all little pieces of R2. So this graph down here is not cellularly embedded. If you take the graph out of this surface, you're left with an annulus instead of a disk. So all the graphs are cellularly embedded. There are different ways of encoding cellularly embedded graphs. It's hard to draw complex graphs on surfaces as graphs on surfaces. And effective notation can facilitate doing the mathematical computations. So let's take a minute here to look at some of the different ways of encoding a cellularly embedded graph or communicating the combinatorial and topological information of a cellularly embedded graph. So if you take a graph cellularly embedded in a surface and you take an epsilon neighborhood of all of the vertices and edges, you get something that's called a band decomposition. So this is a division of the surface into three distinct kinds of regions: the vertex regions, the edge regions, and the face regions. If you remove the face regions from the band decomposition so that you're just left with these disks with edge ribbons between them, you get a representation of a cellularly embedded graph called a ribbon graph. So this is a ribbon graph here. And this is another example of a ribbon graph. This is K4 in the projective plane. So those are ribbon graphs. Even ribbon graphs get tedious to draw after a while and to do computations with. So one of the most efficient ways of drawing graphs on surfaces is something called a disk representation. And for here, we start with our ribbon graph, label the edges, and give each edge a consistent orientation. And now all we need to record are the vertex disks and the direction and number of the arrows where the edges meet the vertex disk. So right here, this edge labeled 1, where it meets this vertex disk, has an arrow pointing counterclockwise, and all I need to do is record the arrow. And that gives me the disk representation, just those 2 little circles with some labeled arrows on them, instead of having to draw the whole ribbon graph. Going back in the other direction, if you've got a disk representation, you just draw arcs head to tail and head to tail to get your ribbons back. Sound good? Okay.
Yeah, that's good.
Good. Okay. Okay, so surface duals are constructed in the same way as planar duals of plane graphs. You've got a graph drawn on the surface, and you put a vertex in each face of the surface, and you connect 2 vertices if the faces between them are adjacent. So these 2 vertices are adjacent through this edge, right? They're also adjacent through this edge. Okay, so you put in the edges. So what to pay attention with here, a couple of things. The graph and its surface dual, or its geometric dual, lie in the same surface. Right? In general, the graph and its dual are different graphs, even though they lie in the same surface. It happens that this example that I've got here is self-dual. The original graph and the dual are isomorphic, right? But that is in general not true. The other thing to note here is that taking the dual has order 2. If you take the dual and then you take the dual again, you're back at the original graph. Right? So it's an operation of order 2 on embedded graphs. Petrie duals, these are also called left-right walks. In a ribbon graph setting, they are what happens if you take each of the ribbon edges, detach one end, give it a half twist, and stick it back on. This is equivalent to looking at the graph in a surface and taking left-right walks as your new faces. So you use the same vertices and edges, but when you're tracing a face, instead of always turning to the right or always turning to the left, when you trace a face now, you follow an edge and you turn to the right and then you turn to the left, and the circuit that you get by doing that is now a new face in the Petrie dual. And you'll see that this business of giving the edges a half twist has that effect. If you start here and you're walking, and you're here, now you're turning to the left to go around. Now you're turning to the right to go around. Now you're turning to the left again. So this, the faces here, if you tried to sew discs into this ribbon graph to recreate the surface, you'd be taking left-right walks. All right, The couple of things to note here is that Petrie duals, these two graphs, have the same underlying abstract graph. They're both K4, but in general, they're on different surfaces. This one on the left is on an orientable surface. This one on the right is on an unorientable surface. And again, the second thing to note here is that taking the Petrie dual also has order 2. If you take the twist of all of the edges again, you get the original graph back. The edge twists cancel with parity. So twisting an edge twice is equivalent to not having the edge twisted. All right, back in 79, this is some work of Wilson, and there's something called the Wilson group, which is a group action on the space of embedded graphs. It's the group generated by taking duals and taking twists. So you take the dual, the geometric dual, you take the twist, or the Petrie dual. Those are both operations of order 2, as we noticed. They don't commute with each other, so they generate a copy of S3, and you have an action of S3 on the whole graph. So these two elements, the twist dual and the dual twist, these operations of order 3, those are called the Wilsonials, and they're trial. Then the other element of order 2 is called the opposite for whatever reason, and it's what you get if you take the dual, twist, and take the dual, or equivalently twist, take the dual, and then twist. So we now have this action of taking duals, taking Petrie duals, taking trials of embedded graphs. And as usual, we're looking for symmetries. We're looking for graphs that do nice things. So you're looking for graphs that are self-dual, self-petrial, self-trial, etc. And in aggregate, we refer to these as self-dual graphs. Right? This graph right here, this is 2 loops in a Klein bottle, and this graph is all 3. It's pretty quick to see that if you twist both edges, the graph that you get is isomorphic to this. So it's self-petrial. It's a little more work to see that it's self-dual and self-trial, but this graph is all 3. It's a very nice symmetric graph. Okay, so let's look at some special graphs. So there are lots of examples out there that are self-dual, but not self-trial and not self-petrial. So B2 in the torus is an example. It's self-dual. Okay. But if you take the Petrie dual, both of these edges are twisted and you can't do anything about it. The Petrie dual's unorientable. The graph itself is orientable. So it isn't self-petrial. It's also not self-trial. This graph here, 2 loops where one of them is twisted, is self-petrial. If you twist both sides, all it does is switch which side has the twist in it. But it's neither self-dual nor self-trial. And then this one, this is the graph we saw a minute ago. We say self-Wilsonial, it's self-everything. It's a lovely symmetric graph. All right, but the last option, the last possibility here are graphs that are self-trial. They have this operation of order 3 that returns them to the original graph, but they're not self-dual and they're not self-petrial. Those guys are really hard to come by. In fact, Wilson hypothesized for years that they didn't exist. Okay. The first example that was found of these graphs that are self-trial but not self-dual and not self-petrial is this thing that you get if you take a tiling of the hyperbolic plane with 9 gons, so where you put 9 9-gons together, and then you take a quotient by identifying vertices connected by left-right walks of length 9, so these Petrie polygons. It has Euler characteristic minus 70. It's got 126 edges. It's huge. All right. Again, the same Jones-Poulton paper, the regular, and they were only looking at regular maps, which is important. The regular non-orientable examples with the greatest Euler characteristic that are these self-trial but not self-dual or self-petrial graph are this graph that we just saw, and it's dual plus double covers of them. And then the regular orientable examples are even bigger. Okay, genus 193, genus 392. Okay, these are really symmetric graphs. They've got the same vertex degrees, the same face degrees. They've got transitive automorphism groups. They're basically using the machinery of regular maps in trying to find these. All right. Why are these things so hard to find? If you have a ribbon graph that is self-trial, it means that if you take its dual and then you give all the edges a half twist, you get the original graph back. But this is a group operation, so that means this being self-trial is true if and only if you take the dual of the graph and you get exactly the same thing if you twist all the edges, which is really kind of bizarre. Especially when you remember that the dual is always in the same surface as G, and the twist always has the same underlying graph as G. But you need these two things not to be G itself. Otherwise, it would be self-dual or self-trial, and we don't want that. We want it only, self-dual or self-petrial. We want it only to be self-trial. Okay? So here's an example. It's not a regular map. It's the small, turns out that, these huge graphs that we just saw, that were the smallest regular map examples. It turns out if you give up the regular map thing and just look for self-trial graphs, the smallest one only has 3 edges. It's this little tiny thing. It's very cute. So here's the smallest example. Here's a graph that if you twist all the edges, you get this graph. And you get the same thing if you take its dual, if you take its surface dual. And this graph is not the original graph. So the original graph is not self-dual, and it's not self-petrial, but you get the same thing when you take the twist and when you take the dual. So here they are in the surfaces. Okay. But this guy is self-trial. All right. So how do we get a handle on these? And how do you find more of them? Okay. So these guys have the same underlying graph as G. They lie in the same surface as G, but they're different embeddings from the original graph. Right? So there's G in the same surface. Here's the same graph embedded in the same surface, but with a different embedding. So our goal was to be able to generate all self-trial, but not self-dual nor self-petrial graphs. So there's this class of graphs that are really lovely, but they're hard to find. But we would like more. In fact, we'd like a systematic way to find all graphs of any kind of self-duality at all. So the fundamental observation is a very simple classical result that's at the heart of all of the computational infrastructure that's going to come. If you have a graph that's self-dual, so for example, H is self-dual, H is equal to what you get if you take the dual of H, and you have some other graph that's in the orbit of H under the Wilson group action. So G is do something to H, take its trio, take its opposite, do something, okay? Then this graph that's in the orbit of something that you know is self-dual is itself self-something. And you find out what that something is by taking by conjugating, okay? So G will be self whatever you get by conjugating by whatever you did to get G in the orbit of H. All right. So here's a graph that's self-dual. This graph here is the twist of H. It's what you get if you give each of the edges a half twist. Okay. But because H is self-dual, this graph here we know immediately is self tau delta tau inverse. Okay, so this is a good juncture to ask what folks are doing. You have questions? Doing okay?
Can I just quickly ask a question? Sorry, since you mentioned that the goal is to try to maybe find all self-dual or self-something graphs, is it even obvious that there has to be maybe finitely many or infinitely many for that matter? I mean, say connected under any, fixed by any of these, duality, triality, or anything.
Yeah, there's going to be a finite. Okay, so we're generally doing this by the number of edges.
Okay, so you fix
for any fixed number of edges.
Oh, you want to fix? Okay, so
yeah.
So you want to fix a number of edges, and then sorry.
Yeah. Yep.
Right.
Yeah. So you'll be okay.
But in general, there probably shouldn't be just finitely many, right?
No, and they just it would be an interesting question to know how fast they grow. Mm-hmm. And I don't know that. Okay, so we have an algebraic framework that is a lot more powerful. It's going to manipulate each edge individually and also handle isomorphisms. And it works by applying the Wilson group operations one edge at a time instead of globally, and by using permutations to track isomorphism. So what does it mean to apply these operations one edge at a time? So this goes back to Shmutov's partial duality and builds an algebraic structure around that. So the way you twist just one edge in a ribbon graph is you just pick it up and you give it a half twist. For a disk representation of it, If you've got the two arrows, you just change the direction of one of the arrows on the discs. So here's a disc representation of this graph, and all I've done is change the direction on this arrow to face the other way. That's how you take a twist just for one of the edges. Twist is, I think, fairly straightforward to see. Taking the partial dual with respect to an edge, but boy, this concept that Shmutov put out just changed the landscape. It's a very cool operation. So the way you do it is, here are the two edges on your disc representation. You merge the two discs, which may be one disc, but you merge these two arcs and put the edge perpendicular, which is kind of what you do when you draw a perpendicular edge and you're creating a dual, drawing the surface dual. So what happens here is, here's the graph. You take these two discs, the disc representation here. You might want to think of taking these two and rotating each of them inward, the one on the left clockwise, the one on the right counterclockwise, until the E1s are facing each other as they do here. And then do the perpendicular transform here. And this now, it's not very circular, but it is a disc. And if you attach the ribbons onto these arrows, this is the result of taking the partial dual with respect to edge E1 of this graph. All right. The nice thing is that if you take the partial dual with respect to all of the edges, it's the same as usual duality. So what's on this slide is the same computation. Up at the top, the computation's just being done with a disc representation. On the bottom, it's being done with ribbons. But here is just a triangle. And we're first going to take the partial dual with respect to this red edge. So we merge these two vertices and put the edges on the perpendicular side. Okay, so now this is a graph with two vertices. Here they are. And if you put the ribbons in, you get these ribbons down here. Okay, so now we take the partial dual with respect to the blue edge. We're going to take these two here. We join the two vertex discs and make the perpendicular edge. Okay, this is now one vertex, and if you attach the ribbons to the little arrows, you get this graph. That's the result of taking the partial dual with respect to the blue and the red edge. And now we're going to take the partial dual with respect to the green edge. This is a little bit different. When we merge these two pieces of the one vertex here, notice that now we've got two vertices. It breaks the vertex into two pieces. And there's the perpendicular edge, the green perpendicular edge. And if you attach the ribbons, you get this, but this outer thing is just a vertex with some ribbons attached.
Joe, wait,
so
I'm
this is
confused.
the same as this. Sure.
Can you explain how we're getting the two vertices? Because I understand that what you're doing is you're merging two different parts of the boundary of the one disc. How is it splitting off into two later when you reattach the edge or something?
Okay, so if you look here, here and here, if these two circles were attached down at the bottom, When you did this game here, it would break it into 2 parts.
Still not following. Where's the break? I mean, because I see an edge there, but the edge is staying in the right-hand diagram.
Yes, the edge is staying there. The edge connects the 2 vertices. Right here, this green edge connects those 2 vertices. The graph is not disconnected. Just the one vertex becomes 2 vertices.
Hate to say it, but I'm still not seeing it.
Okay, hold on for a second here. I'm going to look just at the green bit. There's the green bit. And there's the other green bit. Good so far?
Yes, I'm still not seeing the split though.
Okay. Now, the way you take the dual, I haven't taken a dual yet. The way I take the dual with respect to that edge is I merge these 2 arcs together and put in a perpendicular edge. So I merge those 2 arcs together. And now I put in the perpendicular edge. But in merging those 2 arcs together, because they were originally part of one thing, they become 2 disjoint curves in space. And this right here, as a ribbon graph, is just a loop. This is the dual of a loop. It's a single isthmus.
I get it now, Joe. I think I was confused by looking at the interior of the wrong thing as being filled in.
Ah, beautiful. Okay, are we happy? Well, happy enough. Okay. So, here is the orbit of doing a ribbon operation on a single edge. Okay. So this edge right here, if you twist it, you get this. Okay. If you now take the partial dual of it, it merges the 2 vertices and puts in the perpendicular edge. All right. And now you twist again. It's a little subtle here, but see this region right here? That got the twist. Okay, so from here to here, the loop got a twist in it. Equivalently, we could have taken the bottom root, taken the partial dual of that edge, which merges the 2 vertices and puts in the perpendicular edge. We now twist that perpendicular edge, which puts a twist into the loop, and taking the dual of a twisted loop, it's self-dual, so it leaves you right here, while untwisting the vertex. All right, so that is the orbit of doing these Wilson actions locally. Now, of course, you can do it to any subset of the edges. So now you have what's called the ribbon group, which is an action of S3 to the N. It acts independently on each of the edges of the graph. So you now can take all kinds of bizarre partial duals of all of the edges in the graph and get this huge family of associated graphs of the tools of the graph. Okay, so here's an example of all of this is the full orbit of the graph on two edges. So there's the graph. Okay, here it is down here. If you twist both of the edges, it's the same thing as this. These guys are the same graph. Here's what you get if you twist one or the other edges. We've already seen that if you take the partial dual of one of the edges, you get this graph. You can twist one or the other of those loops, twist both of the loops. So these are all of the graphs that you get by taking any of those 6 elements to either of these two edges. All right. When we're looking at different kinds of duality, isomorphism matters. So if I take the dual of this graph, right, and in this case, we're talking just usual planar dual, take the dual. These two graphs are isomorphic, but not by mapping the same edge to the same edge. I have to map E to F and F to E in order to see the isomorphism. I have to permute the edges. So we would call that graph weakly self-dual, and this graph isn't self-petrial. Similarly, this graph down here is weakly self-petrial. If you twist both of these edges, you get this graph, but in order to map the isomorphism, you have to map E to F and F to E. So it's weakly self-petrial. On the other hand, this graph down here is strongly self-dual and strongly self-petrial. If you take the dual, you get this, and you can map E to E and F to F as your isomorphism. Okay, so what we need now is an algebraic framework that encodes these actions on the edges and the isomorphism. So we're looking at pairs, we're looking at ribbon graphs where we've got the edges labeled. The group acts on the ribbon graph, the partial duality group acts on ribbon graphs with n edges by whatever element of the Wilson group is in the ith position, acts on the ith edge. But we also need to be able to track reordering the edges so that we can capture this weak duality, right? Where you have to have an a non-identity isomorphism in order to see that the graphs are self-dual. And for that, we take a semi-direct product with the permutation group, and all that does is just tracks the permutation. The computation's a pain in the neck, but there's nothing earth-shattering there. So here's an example. Here is a graph with labeled edges, and we want to apply this group element to it. We want to twist the first edge, take the dual twist of the second edge, and take the dual of the third edge. And this is the identity permutation. Let's not worry about reordering things right now. Okay. So here is how you do that computation. Here's the graph that we started with, right? Just this graph. And instead of numbering the edges, I've colored them just because it's a little easier to look at than a bunch of letters running around. So this graph as a disk representation looks like this. I'm now going to apply twist to the red edge. And all I have to do for that is flip the direction on one of the arrows. So that's easy. Done. For the blue edge, I first have to twist, then take the dual. So for the blue edge, first taking the twist is easy. I've just taken this arrow and flipped it to point the other direction. I'm now going to take the dual of the blue edge. And Sarah, this is for you again. I take this and stretch it around. But in order to get these arrows pointing in opposite directions like I need in order to do the dual operation, I have to give this vertex loop a half twist. So now these are facing the right way to put in the perpendicular edge. There it is. And if now I track that loop or that curve around as just a circle, this is the order of the arrows and the directions that they go in. Okay, and that is the dual twist of the blue edge going from here to here. And now you do the same kind of game to take the dual of the green edge, and you get this, which is this graph here, where the little X indicates that that edge has a half twist. So that's how you applied twist, delta to this graph to get this one. All right, so that's how you can apply these group elements, S3 to the number of edges now to graphs. So here's the strategy for being able to get graphs with the desired kind of dualities. I want a graph that's self-trial. Well, up here on this commutative diagram, I put delta tau. Right? I want it to be self-trial. I want this graph here with its labeling to equal this one. After I apply the edge operations to it. In order to play this game, I need something nice to go down here. I have something nice to go down here. I put what I want to see up here, and then I solve for the alpha, the element I need that does the transform. All right. So let me say this again. Staring at commutative diagrams can just be a little mind-boggling. Our objective was to find self-dual, self-trial graphs. Okay? The graphs that we want that are self-trial, that means that if you apply these operations to them, you get the same thing. Graph here, same graph here. Because of the group operation, there's this nice commutative diagram that lets me put a well-behaved graph down here and solve for an element here that will get me the graph with the desired property. This reduces the problem to part one, find something convenient to put here. And convenient turns out to be as simple as graphs with just one vertex. So the entire theory of graph duality of any kind can be captured by one vertex graphs. Every connected graph has a single vertex orientable graph in its orbit. You just keep taking duals until because when you take a dual, it merges two vertices together, and you just keep doing that until you've sucked everything together to a single vertex. Furthermore, all forms of self-duality propagate through the entire orbit. So you can if you can identify the self-dualities in those single vertex graphs, you know all of the self-dualities in the entire orbit. And that is the lovely thing, because finding self-dualities in single vertex graphs means just dealing with chord diagrams, which reduces the isomorphism problem to just looking at dihedral groups, symmetries of the dihedral group. So instead of looking at all embedded graphs and having to take duals and check for isomorphism of just these huge embedded graphs, all you have to do is look for isomorphisms in the dihedral group. So you enumerate irreducible chord diagrams. Those all correspond to your irreducible single vertex graphs. And do the partial duality operations and check for isomorphism just by checking the dihedral group symmetries. So, yeah, there it goes. And now what we do is down on the bottom, you take any single vertex graph with any kind of self-duality, doesn't matter. You're just glad that you found some kind of self-duality. You put it down here. You put the kind of duality that you want up here. In our case, these Wilson, these self-trial graphs, we put that here, and then we solve for the element that takes this well-behaved guy up to the guy we want. And it turns out to be quite quick to solve for these. It's linear in the number of cycles of the permutation. So that's lovely. We find all of the stabilizers of those one vertex graphs, and then you play, right? You want a self-trial graph with 3 edges. You start with any 3-edge single vertex graph with some stabilizer, and you run through a solver to find that alpha. And it's bounded by what, 6 times, yeah, I guess 6 times the number of cycles in the permutation. So here's an example. Here's a one vertex graph, okay? This graph right here, if I don't do anything to the first edge and I take the partial dual with the second and third edges, I get this graph back again. If I want a graph that's self-trial, I want a tau delta, tau delta, tau delta. I put that into the top of the commutative diagram. I solve for alpha. The alpha I get is tau delta, tau delta. I now apply this to my original graph, and I get this graph, which is self-trial. It's different from the one we saw previously, and there are 5 other solutions. So it exhaustively finds all of the possible 3-edge graphs. All right. Yeah, 3 edges is not all that great. So this is an exhaustive list of all the SFOGs that are self-trial, but not self-dual or self-petrial. And we get a complete list of self-trial graphs for each number of edges. And I can't remember when we got tired of running the program, but it generates all self-trial graphs up to, I don't know, 8 or 9 edges at this point. But exhaustively, all of them, it just goes through. I'm going to not do the power of automorphism, but simply mention that instead of putting one vertex graphs at the bottom, you can instead not do any twisting or dual of the edges, but take advantage of the automorphism group. Just change the permutations. And now you can play that same game. Your something nice down here is just an element of the automorphism group. And this reveals why regular maps which have these huge automorphism groups, were a rich field for looking for self-petrial, self-dual kinds of graphs, is because you can play this game with the automorphism group. And infinite families of graphs that are not self-dual or self-petrial, they don't need to be regular maps, and they can have very small characteristic in genus. So take home is that there are now systematic tools to study self-duality, and on any kind of graphs, not just regular maps. The information is encoded either in these single vertex graphs. Let me rephrase that. The information is all encoded in these single vertex orientable graphs, but you can also get at a very rich field of information from graphs with nice automorphism groups. Okay. Thank you very much for your time.
Thank you very much. Zoom clapping. Let's take questions, and I will stop screen recording.